Hello, this is the notebook, the Jupyter notebook presenting the work that I've done so far in trying to analyze the data and predicting the model according to what you gave me, the data we got from the World Bank database. So how does this goes? So it goes like this. First of all, we do have to set the stage. I want to exploit the my wide screen. That's why I set up this is just to tell the screen that the notebook that you are on wide screen, please use 95% of the width of the screen. Then I import the needed tools, the system where to I go to fetch the file. I need this module TensorFlow Keras. I need Panda for data importation and data manipulation. I need sklearn. I need TensorFlow TF. This warning is just to avoid the red line coming out and so on. This is the type of model I'm using, a sequential, and the type of neural network I want to use, a dense neural network, meaning that the interconnectivity must be a lot intense, and also it must be dense, and it has to have an activation function. I'll show you that in the network when I write the function. It is down below. Okay, so here is where we start. I need NumPy because I'm manipulating the table. Seaborn is just for plotting the figure. You will see there are a lot of plots. And sklearn metric is for evaluating how the process of learning. I want to establish one thing is to show, for example, what are the tools I have. For example, I have TensorFlow 2.4 version that I've installed. Keras is 2.4. Python is 3.8. And I have Panda 1.2 and so on. Okay, this is all. I don't use the GPU programming, but because I didn't bother to reinstall Python on the GPU, but I can do that. Okay, this is the set of data we have, the files we got from the World Bank. We have the file for the DRC, for Ethiopia, for Nigeria, for Tanzania, and for South Africa. So I imported this file. While I import them, I want to see how big they are. South Africa has 1,443 rows and 66 columns. It means that the data is for over, I think, 61 years, and going back to 1960, as you will see. And I have Nigeria the same. 1,443 is the number of indices, these indices that you see, commercial service, export, and so on. So these indices, here I'm just displaying the 5 row of the data, but you have these row, you have them labeled from 0 to 1,442. Of course, this is, I just displayed the South Africa. I can do this for all the data. The first problem I met is this. And this is not just the problem that you have in this data. This is a common problem for any data that you get. You have the missing. So the first treatment that you have to give to your data is how do you deal with the missing? For example, you can see here in South Africa, in 1960, there are data missing for ores and metal exports in percentage. Missing from 1960, 1961, 1962, 1963, 1964, 1966. Of course, you can even have more because you see some lines here are broken. And then you have for 2021, you do not have that and this as well. So you can see also, for example, here, urban land area information missing all the way. You can see all the way. So like this row of urban land area, there is no information at all. So definitely this index will be useless because it doesn't have data. So I have all the data. The first thing I want to do is to find how much is missing in each data set. So for South Africa, I named this meeting. I call this function, I make it, I found everything that is missing is now sum up for each row, for each column. And you do the same for the Nigerian data, for Tanzania, for Ethiopia, and for Congo. After that, please plot me the picture of everything missing. For example, for the DR Congo, you see, we know that there are how many rows? They are 1,443. For example, you see how many is missing in this. In 1990, I just take the data from 1990 onward. In 1990, there are 400 entries that are missing, meaning 400 index, and this is were not entered in the database. In 2000, almost 600 or 500 is missing. And you have this. This is for the DR Congo. For Ethiopia, you have the same year, 200 and something, almost 300, and there almost everything missing for 2020. The same you go all the way for every country. So in data analysis, when the data is missing like this is a problem. It needs to be addressed before you continue, you do anything else. So now I say, okay, let's set a threshold where we drop for every, because we know that we have how many years from 1990 to 2020, we have 30 years. I say for the data set, please, if you found any row missing 60 data entries, drop it. Don't consider such a row, meaning that remove all the rows from the data that has more than 16 data set entries missing. Meaning that when you look at your Excel sheet, you look in each row. We have, because I cut from 1990 to 2020, I have 30 years. In the 30 years that is, if you found there are empty column, 16 of them, please forget about that row. And I do this. I create this data set and I do the same. I say, okay, take 20 or take 18. What do you want? For me, water. I'm doing something. Can you see? Ask your mother, please. I cannot because I put the cream on my legs. Okay, so we continue. So I do this. I put different threshold. And now you look. For example, when the threshold was 16, how much do I have? I have for South Africa 967 row for 33 column, while DRC is 785. While you have for South Africa in the 20, you have 611, 875, and so on. So you see, this is the data I have. Now I say, okay, let's drop those rows and see how much is missing. For example, if I consider the data for 25 years, for 25 years, how many missing? And for 18 years, how many missing? So I plot those graphs for each country with all the sort of data set. So you see, the more less year I have, like when I have for 18 years, I have less missing. More year, more missing. Now, remember, we saw that, for example, for DRC, there were 600 row, while 611 and 785, while for South Africa there were 800 and something. So we need to make uniformity. So we need to have the same type of data for us to train the same model to analyze all the country. Therefore, I do uniformization. I write a function here. This function is an intersection. I take the list of rows, I make intersection like we used to make intersection of set. I tell this function say that please pick all the list of rows that belong to each country, each of these 5 countries, and only return to me the rows that are common. For example, if I take for 25 years, only 55 rows are common. If I take over 18 years, only 53 rows are common. So I want to use these 53 rows or those 55 rows to do my analysis with. The rest of the indices, I throw them away because they have too much missing. So I do that. When I do that, I check. So this is the data that is remaining for the 18 years. And this is how it looks like. Now let's try to fill the missing. I fill the missing. For me to fill the missing, I write a function. This is the function for solving the missing problem. So I say, pick in the data set, look at the column, go through each one of the column that have entry data, because the two first column, this one and this one, they have the indicator name and the indicator code. They are always filled. There is no missing, but it is only starting from here to the end where they're missing. So pick from the second column all the way, from the third column all the way to the end, and fill the missing value by the median. Why I choose the median, I'll show you later. The median, what is the median? When you take a distribution, the median is the line that cuts the distribution by its middle, by choosing the middle. For the normal distribution, the Gaussian, you have the median and the mean are coinciding. When you take the skewed distribution like the one we have in this case, you will see why I'm saying it is skewed distribution. The mean is a bit ahead of the median. So I choose the median because the median helps not to shift, not to tilt the distribution. I don't want to cheat with the data. I want everything to reflect the reality. So that's why I choose the median. I fill the data. After filling the data, I work out everything. And now I'm plotting now the KDE, the kernel of each distribution. You take the data, for example, for the DRC. This is the kernel of the distribution between 2000 and 2003. So this is how the kernel of the distribution looks. What is the kernel of the distribution? Every data entry, when you take every data in a table of data has a certain probability according to the column, has a probability in the column. So the kernel represents the probability of a value in each column to be there. And as you can see, the majority of the values are around 0. There is some value with -1 and some value are very big. This is 6 times 10 to the power 12. What is this value like? This is like 6,000 billion. So 6 trillion. So you have the data that range from -1 to 6 billion by value. And this, I am pointing out this value because I want to explain to you why I use the Z-score. So you see that the data have a wide range of values. Now, when you do the analysis, because when you do the analysis, what we are doing prediction. This prediction is like a regression. It is like I choose certain data which are like X coordinates, and 1 year is like the Y coordinate. I use the X coordinate to predict the Y coordinate. But if the range of values is so wide, like one value is as small as 0, the other value is as big as 6 trillion, you see that the value that is bigger will always drive the prediction. And this is not good in data analysis. That is why you need to use the z-score, because the z-score is like you take the value, you subtract it to the mean of the distribution, then you divide by the standard deviation. Then you will see that the range between the higher value and the lower value is shortened. You will see that below. So I write a function that does the z-score normalization, and I work out that. Then I plot the z-score. You see, first of all, the z-score doesn't destroy anything, because you see the distribution is still the same school distribution. The smallest value is -2, while the highest value is 8. You see, we were from -1 to 6 billion. Now we are between -2 and 8. You see how the z-score score fix things. So that is how I'll fix the stuff at this level. Then we move forward. Now we do feature engineering. I explained to you that when I pick the data, I have to create one row which will be predicted, which will depend on the other row. Meaning that I have to pick 1 year and then work out the outcome of that year, the indices, the indicator of that year, by using the indicator of the previous years. This is how I set up my neural network. I train it to learn to recognize that because I have this in the past, this is what will happen in the future. So it learn like that. It make the weighting of the connectivity, the neuron connectivity. It make the behavior. It teach the neuron how to recognize. It is like the human brain work. We work with the neuron. How do we work with the neuron? How do I recognize, for example, the face of someone? When I look at the face of someone, they are spot on the face that are differentiated the person from another one. So my neuron fire when they see those spots, and they memorize that the function, the value of the function, that of the power that goes through my neuron to fire this memorization is kept, so that next time I see the image of that person, I will associate the name with that person. The same way we teach the neural network to recognize like that. So that is what I'm doing here. So the first thing is I create the x value by creating a feature engineering. So I break the data. I take the data that is, for example, 18 years or 25 years. I take 24 years I put together as x-axis, and one last year as y-axis. The same I take, if 18 years, I take 17 years as x-axis, and y-axis I take the 18th year. So I do that. Now there is one more trick in the basket. The trick in the basket is that, remember, we have on one side dependent variable and on another side independent variable. So, but dependent variable should be independent, meaning that you cannot have among the x's x behaving like they know each other. So how do you do this in terms of data? You work out the correlation between the the column of your Excel table. So this correlation is in terms of year, correlation between 1 year and another. Wherever you see the bar of correlation goes from 0 to 1. Wherever you see red, it means there is very, very strong correlation, which is not good, because you have to have independent variable. Independent meaning that each year must not never depend on the other. But here we see that each year is depending on the other. This also can destroy the prediction. So this is not good. In geometry, I don't know if you remember your geometry very well. In geometry, you have the system of axes. We used to have the system of axes with no right angle between, or you have the system of right angle. If you have the system of right angle, then the projection, the orthogonal projection gives you 0, meaning that there is no correlation. But if you have the system with an angle of making something, when you do the orthogonal projection, you always get the value of one axis into the other. So here, this is what you have. You have non-orthogonal system. I want to create orthogonal system. So how do I do this? I apply principal component decomposition. It is a statistical method, and I do that. This is an orthonormalization. As me as physicist, I would call it an orthonormalization, meaning that I'm destroying all the correlation between the dimensions. So I do that because here I had 18 uh, 18 years, the same. I break this function. I introduce that. I say, okay, take the 18, create new 18 years components that are not depending the same. So I create that, and as you can see, the heat map of the correlation here, strong correlation in the middle, in my 18 new components, orthogonal, no correlation, only autocorrelation. Autocorrelation is normal because autocorrelation is the correlation of the dimension and itself. This should be 1. As you can see, it is 1. While correlation between dimension is 0. You can see everywhere it is blue. So this is the where uncorrelated dimension, while on top I have correlated dimension. You can see that. Now let's move. Now we go down, and because I have this now, I plot again for the 25 dimension as well, so we get this. Okay, now let's try to set the variable. I set the variable such that I have, remember, the neural network doesn't work with the data frame. It only works with the variable as integers or as numeric numbers. So I have to remove anything that is non-numerical. That is why I put them in array. I remove them from being Panda object, Panda series, into becoming NP array in Python by making them values. So that is it. So I do this. I break all the that I have. For example, a Congolese field, I have 25 years of. I create the X and the Y. The X and the Y. As you can see, what is the X? The X has how many? It has 18 row, 53 row, 18 column, while the Y has only 1 row, two column, but one column is the one I'll predict now, the other is the one I'll predict in the future. So you see, these values are Z scores. They are not the value that I had in the beginning, because I remember I put the Z score in order to reduce the stretch between the lower value and the bigger value. Okay, now we go here. Here now I use the sklearn to break the data such that I have a set of data, a group of rows that I use to train my neural network, and another group to test if the neural network works. So I said, take among my 53 row, take 25% of them, keep them away as my testing set, and 75% of it, use them to train my network. So the network has to go through my 75, train itself, and learn to recognize the future from the present. After that, I will test its knowledge by feeding it the data that the 25 I kept for testing, and see if it can predict very well what it was in the Y for the test. So as you can see, I have X for training, X for testing, Y for training, Y for test. X for training, use Y for training to learn how to identify the future Y from the present X. While X testing is used by the model, I feed to the neural network the X for test, and it predicts me some value, and I compare those values to the Y. I see how much they look alike. So now let's build the neural network. So I'm building the neural network like this. I create my neural network such that the first line of neuron, so just imagine, I saw you draw it in your paper. The first line of a neuron has to have 16 neuron, 16 nodes. After the 16, I inner layer has to have 25. So I have like 16, then 25. Then I take from the 16, I have the neuron that goes to the 25. And then from the 25, I bring them back to 10. So I have 16 line connecting. Then I have from 25, I break them down to 10. Remember, this is a dense neural network. It means that for each bubble in the 16, it is connected to the 25. Then from each 25, it is connected to the 10. So I have this, and each neuron will learn now from that. And from the end, I take the 10, I bring them into 1. So I have like 16, 25, 10, and 1 at the end. I will have the time to draw this for you, but first I was more busy with this. I hope you understand. Let me draw it here on the book, and I'll show you. So I have like neural 1, bubble 1, 2, 3, all the way to 16. Then I have second row, I have 1, 2, all the way 24 and 25. And then I have 10, 1, 2, 1, 2, and all the way to 10. Then I have the last one, which is 1. So I have like this is connected with all of them. This is connected with all. So I have like, I hope you can see how God, yes, I can see from here. So this is connected with all of them as you, let me try to find the camera. And then this will be connected with all of them. And then this will be connected. So this is how the neural is. So you just connect. So the first layer here is 16, then the second 25, then the third is 10, and then the last is 1. So you have all connected like this, dense neuron. That's what we spoke about. Okay, then after I've done that, now I feed the data for South Africa. For 25 years, I feed the data for South Africa. This is how I feed the data for South Africa, I say. I input the X of South Africa. The activation function is called ReLU. What is a ReLU function? The ReLU function is the function like this. It is a function like this. It means that it is 0 all the time, but when the value is exact, it fires. Just like neuron, it is like it sends a signal somewhere. So, and then I tell the neural that take 1,000 epoch, so learn 1,000 times till you recognize, but each time you have to calculate the loss. When the loss becomes stagnant, stop. So that's what I'm telling it. So I'm telling it that have a patient and learn 1,000 times, and what you monitor the epoch with the callback, and when the number of epoch is enough, then make an early stopping. That is what is written here. So I run that. As you can see, I start epoch 1. The loss is 0.190, and this is the value of the loss, and then you have the loss. Then you keep going, we keep going. Once we arrive here, you see we were going 29, 20, 35, 29, 28, then we go back 30, 33, 35. It seems like we are no more learning. We have stopped learning because the neural is no more learning, so it stops there after 10 epochs. So because it has learned, okay, now I ask it, okay, take the test X, predict what is the score. It work out the error, the mean square error. You know how to work the mean square error. It means that you take the difference, then you square. you square and then you take the difference. So the mean square is 0.0035 and so on, all the long number. I say, "Coach, this is not enough. Please, can you work out what is the root mean square?" The root mean square is always better. The root mean square is mean that you take the square of the value, then you work out the square root of the error, and it works out, it found that this is the root mean square. Okay, that's fine. It is almost 0.6. Look at this value, almost 0.6. Now, work out the chart of the predicted value compared to the normal value, the real values. So this is the expected value is blue, the predicted value is red. You see the difference. So in the beginning, the prediction has a difference a bit bigger of 0.1, and then it becomes very small. This value is almost like, if you check the difference between -3 and -3, this is almost like 0.35 or some 0.5 or even less. So you see the prediction, how it goes with this. So this is why I say that the prediction was very good. Now let me change the value here. I will feed it different value. Instead of South Africa, let's feed it, for example, the value from Tanzania. You will see the prediction, and we run the code again from the beginning. Okay, to run the code, you go here, kernel, and then you run everything. You have to restart from the beginning. I will, when I'm done everything, I will just show you how you can save the training, and then the model will you can just use the code from the time you saved your training. So it will take time for it to work. As you can see, let's go from the beginning. You will see how much time it takes, but not much, maybe 10 minutes. Oh, okay. So you see, the first row is already run. Okay. Couple of more rows run. Of course, now we see it will plot. Yes, it plot the missings. We go all the way. It has plotted all the way, and now, yeah, it has plotted missing here, and we can go now. Of course, we're filling the missing now. All the way, we still going. Here, for example, yes, now it has plotted this KDE. Let's go, and now it has plotted the Z score, and yeah, all the way. So here we still have now to plot the heat map of correlations. You can see it has not plotted yet. It will plot, and you will see heat map of correlation. This shows that the code is still busy. You can see here where the mouse is circling. Okay, you see now the correlation function have run. For Tanzania, for example, and for DRC, you can see the code, and okay, now we go all the way. Yeah, for DRC, for example, for South Africa, we saw it stopped at 10. For DRC, for Tanzania, it goes all the way to 29 epoch, And whoo, there is something wrong here. Something wrong. No, there's nothing wrong. There's nothing wrong. There's nothing wrong. It is the scaling. You see, the difference between the predicted and this is 0.370. This is minus 0.355. So in terms of scaling, the difference here is 0.025. So the predicted and the expected, the differences between is like 0.025. Let's work out the root mean square. This is 0. Almost 2, as you can see. So the prediction and the expected are very good. The value are very, very close, you can see. It is up to the hundreds. You can see the difference. If I, for example, I change, let's say, y limit. Let me do the y limit axis, limit the y-axis. Let's try to limit the y-axis in terms of range. Okay, let's set the y limit here so that you see exactly what I'm talking about. Oh, I must go with the minus as well. So let's say from minus 0.5 to 1. Okay, you see, now that I've scaled the axis differently, you see how the values are close to one another because the scaling was wrong. That's why you didn't see. So this is it. So I'm sending you this video 38 minutes so that you see what is going on. Okay, have a good night. Oh, by the way, I just want to show you what I'm doing, what kept me for many days. So here I restarted. I was trying to find, because I have to find a way to reverse the Z score in order for you to be able to show that this is what we predicted in Z score. In reality, they are equal to this value. Z score statistically mean that you take the value, you subtract it to the mean of the distribution, and you divide by the standard deviation. The function that is I use in Python is worked. When I do the z-score by hand, the answer is good, but I'm not able to find the consistency because of the shape of the data. So I was fighting with this, and I found another way of also presenting them and so on. So this is what I've been fighting with, and I did use other method. This time the data I had more line because I had like 1,154. So this is what I wanted. This is the final product. This is what I'm working on right now. But I'll send it to you once I'm done. So, but I just send you the first video so that I can show you where I am and where I've stopped. Okay, have a good night. I'll send you this.